Drop.
Drop, probably. Wait,
So tail light will drop
really?
today.
Oh,
Today.
we made it.
No, it's just it's Halloween too, so.
Alright guys, too late, huh?
It's too late.
Too late to drop. Oh no, it's tail light today. Today. Oh, so after the class you can still drop it. All right. So last time I did a test code. So basically you have a circuit on top of the other, and this could be the load. This could be the driver, or vice versa. Okay. And then typically the output is taken from here, and the input is fed to the driver. Now again, the load could be on the bottom, okay? The driver could be on the top. But it doesn't matter where you have the load and the driver. The load always has the drain connected to the source. Got it? Remember? It's this. Okay, so the load always has this type of configuration. It's a very important example. You should make sure you study. Okay, something's similar pop up in the exam. Okay, so that's one of the multiple stage amplifier connections. The second widely used connection is called cascade. So basically, you have one circuit, you have a second circuit, then here's the output, and then here's the input. Okay, then the connection of the two circuits could be either a capacitor coupling, C, or a direct coupling. Yeah. So I remember in the bipolar amplifier, we talked about the case of the capacitor coupling, right? Okay, so in this chapter, I will try to talk about the direct coupling, right? There are pros and cons for each one. The pro for the capacitor coupling is that the first stage and the second stage are independent. Yeah, as far as the DC is concerned, yeah, because this is open. But you do have to put a capacitor, and the capacitor can have some parasitic effect. The direct coupling does not require capacitor, but you can make the DC analysis more difficult, right? Because the first stage is connected to the second stage. Okay. So today I'm going to do an example on the direct coupling of cascade. But before I do that, I look at a note before I came here. I thought I should do a single stage, so I'm going to go backward. Okay, I'm going to do a single stage that has almost everything, because I feel more comfortable if I do the example, so that you will understand how to analyze a single stage with the most difficult problem. Okay, it has everything, right? So that's what I'm going to do now. So this is the case I'm talking about. over here. See, typically, by the way, this is called a common what?
Common
Common drain, right? Yes, because the output is taken from the source. Okay. Typically, I don't know if you notice. Typically, when I do a common drain amplifier, there is no resistor connected to the drain. Okay, this is always a short circuit. To make it simple. Okay, but this time I try to make it more comprehensive. Okay, so you do have an R sub D. Also, you notice before, most of the time we don't have R sub X here, right? Okay, so by adding these two resistors, this circuit is more complete, but the analysis will be more difficult. Okay. I don't have to go through the DC, right? Under the DC, this is open, right? So R sub X has nothing to do with the circuit. So I just go to the AC, correct? All right. So connect to the gate, correct? Okay, and you should have this guy here, R1 in pair with R2. Yes? Okay, and the source. Yes? To RS, to the ground. The gate, the drain, right? The drain is connected to R sub D to the ground. Yes? Okay, then the model. I'm going to also throw in the R sub O to make it even more difficult, right? So as far as a single stage is concerned, I don't think there's anything that's more comprehensive than this. It has all the components, even R sub O, right? Okay, where's the output? Right here, right? Okay, so let me just derive A sub V and A sub I, right? Okay. So first of all, what is V sub O? There's a current, all right? There's a current going through here, which is not known at this time. So I'm going to have to call this like V sub prime, correct? So therefore, the current going through R sub S is what? Is V sub prime R sub O plus GMV GS, right? That's the current going through R sub S, correct? Times R sub S, and that's equal to V sub O, yes? Or as I said many times, the key is to try to express V sub O in terms of VGS, right? So now you have a V sub prime, so you have to try to find a way to get the expression of V sub prime as a function of VGS. Okay, now if you look this loop, So this current going through R sub D is that current, right? The same. Correct? It's the current going through R sub D, right? Also going through R sub S, same current. Okay? Plus B sub prime. This is plus minus, right? Plus B sub O, yes? Which is this? Equal to 0. So now you can see we have B sub prime and VGS, right? So now I can try to get an expression for B sub prime as a function of VGS from here, right? So it's going to take a while, but at the end, you'll find that B sub prime is equal to okay? It's nothing but algebra, huh? From here to here. So now, I put this in here, right? I would have everything in terms of GS. So B sub O is equal to, I have to tell you it's quite messy, isn't it? But again, at the end, that's what you're going to have, okay? Okay. Now, of course, everything in the bracket is supposed to be no, huh? Right?
Sorry, is that minus?
This one? Yeah, it's a minus. Okay. Now let's go to see if we can find A B sub I as a function of VGS. Yes? Okay, so let's call the current I sub I, right? Right? So you know I sub I should be equal to B sub I over R1 imperial R2 plus R sub X, correct? So therefore, B sub I can be expressed as a function of I sub I, right? I sub I, R1 equals R2 plus Rx. So now the question is, what is the relationship between this I sub I and the VGS? Right? Okay? Now, you should know that V sub I is also equal to this plus this plus this. Huh? This is the sum of the voltage drop here plus the voltage drop here plus the voltage drop here, right? Or in other words,
The voltage in R1 and R2 is the same.
yeah. So in other words, you can do the following, right? You can say I sub I times R1 in parallel to R2, right? Should be the same as
VGS plus.
VGS, right? Plus E sub I, which is given here, right? So V sub I is R sub S times V prime R sub O plus GM VGS. Now I think it's better to do the following, okay? This is V sub O, correct? Yeah? Yes? Okay, and I have an expression for V sub O. And let me do the following, okay? Simplify my writing. So let me call this A, can I? Because basically it's a constant, right? If you plug in all the numbers, it's a constant. So V sub O is basically A times VGS, correct? Okay, so I sub I then is equal to A plus 1 VGS over R1 in parallel with R2, right? So now you put this here, yes? So your V sub I will be equal to A plus 1 VGS R1 in parallel with R2, right? Times R1 in parallel with R2 plus R sub X. Yes? So I put this here, right? And that's what I have. Okay, then now I can take the ratio, right? V sub I on top, V sub I on the bottom. So VGS will cancel, right? So we get A plus 1 R1 equals R2. R1 equals R2 plus R sub X, right? Divided by that. Oh, what we're doing here.
You do the
This
V.
should be on the bottom, right?
Yeah.
Okay, so it's on the bottom. Alright, that's the denominator. And the numerator is Z, right? Got it? Huh? No, so this is a line. So this is like a generalized formula, huh? Right, if you have a circuit like this, and if some of these components are, let's say this one's 0 or this one's 0, you can use the formula, just plug in the, right? You don't have to derive anything. because I gave you the most comprehensive formula, most comprehensive solution. But remember, this has to be a common trend, right? If it's a common source, then this formula will not apply. Huh? Okay, so let's say what is A sub I now, okay? So this is A sub B, correct? So A sub I, so we're talking about the current here, right? I out, I in. So what is I out? Oh, actually we have it. What is I out? I out is this guy, isn't it? What? Right? It's this guy, right? Is that? No.
The negative of it,
Yeah, the negative of it. Yes. Correct? Because V prime is the voltage drop. So the current times V R sub O is the voltage drop. V sub prime. So that's the current going through R sub O. But then if you're talking about so this is no, right? So I sub O, so let me go back. So I sub O has two components. Has the did I ever say what's the let's call this I sub prime, right? So I sub O is I sub prime, which is minus, right? It's minus I sub prime
Minus G.
plus minus, right? Minus GM BGS, correct? Because if you look at the note on the top. Okay, and I sub prime is what? I sub prime is actually this guy. Yes? Correct? So it's
It's positive.
it's R sub S G sub M. Did I call this plus R sub B G sub M? I put the minus sign together with the minus sign, right? So it becomes positive. Yes? BGS minus G sub M BGS.
If I O is the output current, shouldn't that be across RS, not the RO there? Since we're measuring IO across RT, wouldn't it be across RS instead? Or I guess mistaken.
Yeah, the I out.
And it's across the.
Oh, it's the same. Right?
Oh, yeah.
It would be the same.
Yeah.
It's the same.
But you don't need the negative sign in that case.
You mean this current?
Yeah, so that's
It's
confusing.
also the opposite to this, this opposite sign. Yeah. So if you want to do that, let me
Then
see.
we keep that term negative.
You don't.
Or it would stay in its current form.
Well, to make it simple, okay, you can say I O is equal to minus V O over RS. Correct? Minus, because this is V O, right?
Yeah.
Correct. And V O is equal to A VGS, right? Divided by RS. You want to do that. And that should be the same as that. Okay? It doesn't matter how you do it. Okay? You should have a unique solution. Right? There's only one solution. Okay, so there, everything is a function of VGS, yes? Got it? Okay. What about I sub I? We have solved that already. Good news, right? I sub I is here, right? It's A plus 1 VGS R1 equals R2, yes? So you take the ratio, A sub I is the top divided by the bottom, right? So it's RS GM, RE GM. I don't think anybody liked it. Okay, right? Any question about this? If this is a common source, then the output will be here, right? Is it? Instead of here. Yeah. But the concept is the same. No question? Yeah?
What in your base of I equation on the top of the main fraction, what is the bottom fraction?
The bottom right here?
Yeah.
The bottom is the same as here. Yeah. All right. So now let's do an example for the cascade amplifier. Huh? Question? Oh, okay. R1, R2, RS1, RS2. This is a coupling capacitor C. This is the input voltage. This is I. Okay. So this is a what is it? This is a common drain amplifier, right? The first stage is a common drain. The second stage is also a common drain. Huh? So let me give you all the components. R1 is 454 k ohm. R2 is 1.5 mega ohm. RS1 equal to 20k. RS2 equal to 6k. Okay. VDD, the supply voltage is 10 volts. Kn2 equal to Kn1 equal to 200 microamp per volt square. The threshold voltage is 0.8 volts. Okay, so that's it. So let's try to find IP1, IP2. So this is IP1, right? This is IP2. Yes. Let's try to find AB, A sub I. Right? Let's try to find output resistance of the amplifier. And let's try to find the maximum output voltage swing. Good. So first of all, you would have to do the DC analysis, right? Okay, because this is a direct coupling. How come I can turn it off? Okay, so it's a direct coupling. So that means the DC biasing of the second stage is affected by the DC of the first stage, right? Okay, because it's not open, right? So you would have to do the DC analysis of the first stage first, right? And then progress to the second stage. You notice that because there's no capacitor coupling, it's direct coupling, so you don't need R1 and R2 set for the second stage. Remember, when we did the capacitor coupling, you need one set of R1 and R2 here. You need a second set of R1 and R2 because you need that to bias the second stage. But not anymore, right? Because it's a direct coupling, right? Imagine if you put a capacitor here, right? And you don't have R1 and R2. What's going to happen?
Won't turn on.
You have no voltage here, right? So that becomes a problem. Okay. So as I say, you have to go to the first stage first, right? Okay. So this VGS1, right? It's VGS2. Okay. And you know the voltage here, right? That's called VR2, right? So VR2 is equal to VDD times R1 plus R2 and R2, right? Okay. So therefore, I would get anyway, it's 10 times 1.5 meg. What is that? Is it
1500 kilo, yeah.
K, right? Plus 454K, yes, KK. Then you have
1500K.
you have R2, that's 1500K. Yes?
$7.67 volts.
Oh, how much?
7.67.
Okay, thank you. 7. All right. Once you have that, then if you go around the loop, right here, so you have VR2 plus VGS1 plus ID1 RS1, that's equal to 0, yes? Okay, so you have 7.7 plus VGS1 plus, well, what is ID1? I can assume it's the same situation, right? So it's KN1 VGS1 minus VPN1 square, right? That is the formula for ID times RS1, which is given is 20K, that is equal to 0, yes? So remember, this is ID1, huh? So from this equation, you can calculate VGS1. So let me see what is my VGS1. VGS1, I got about 2 volts. Okay? Of course, you should go and double check, okay? So once you find VGS1, you can calculate ID1. Yes? Put this here, right? And you will find ID1 equal to about 0.3 here. Okay. So that's the first stage. Now, we can move on to the second stage, right? So this, I need to give a name, huh? What do you want to call? Can I call this VG2? Okay? Good? So, VG2, huh? VG2 is the same as ID1 times RS1. Agree? Right? I'm talking about the voltage drop here, right? ID1 times RS1 is the voltage drop here. That voltage is the same as the voltage here, huh? Right? So it's equal to 0.3 times 10 to the minus 3 times RS1. That's 20K. So it's 6 volt. Yes? Okay. Is that my phone or what? Okay. So VG2. Then if you go around the loop here, right? This loop. Okay? So VG2 is equal to am I making a mistake here? Yeah, this should be minus, okay? Yes? Because it go around loop, right? So this should be minus. So that should be a minus. Okay, got it? I hope this is still correct. Okay? So the same for the second loop, right? The second stage. So it's minus VG2 plus VGS2, right? Plus ID2 RS2 equal to 0. Yes? Okay, and ID2 is equal to KN2 VGS2 minus VGN2 squared, right? So you combine the two, right? You get a single equation with VGS2 as down low. So let me see what number I got. So I got VGS2 equal to 2.4 volts, right? We need to go back and verify the assumption where we have assumed that this and this guys are in saturation, right? Because you look at the equation we have used. So therefore, what is VDS1? VDS1 is
2 volts minus.
is it VDD minus VGS2, right? Is it? Because this voltage right here to the ground is VGS2, right? So this is that minus that, okay? And therefore it's equal to 10, right? 10 minus, what was VGS2? I'm sorry, not VGS2, what? VG2, yeah. Mistake here. VG2, all right? Now you have to know VG2 is not the same as VGS2, right? Okay? Okay. So VG2 was 6, right? So this is 6, so it's 4. So is it larger than VP set 1? So what's VP set 1? Is VGS1 minus VPN1, right?
2 minus 0.8.
So VG, this is 2 minus 0.8, so that's 1.2. Well, so yes, it is, right? It is larger. And you do the same for the second stage, right? For the second stage, we're talking about VDS2. What is it? It's VDD minus what? Minus ID2 times RS2, correct? This is the voltage drop on RS2. Okay? So it's 10 minus ID2. Did I give you ID2 yet? Okay, from here you can get ID2, right? So ID2, let me give you the number for that. ID2 is a 0.5 milliamp. Okay, so this is a 10 minus 0.5 times 10 to the minus 3 times RS2, that's 6K, yes? 6K, so it's 3, that's 7 volt. Alright, and VD set 2 is equal to VGS2 minus VTN2, right? And VGS2 right here, right? 2.4 minus 0.8, so it's 1.6 volt. So therefore, again check, right? Because this is larger than that. Okay, so we are in good shape for the DC analysis. Now let's go to the AC, right? AC. When we did the BJT amplifier, we divided 2 stages, right? We would do the second stage first, right? For the AC, okay? And then we move on to the first stage. For the MOSFET, for the FET amplifier, because it's a direct connection, we typically just solve the circuit one time, okay, without doing the 2 stages, okay? So we're going to do the analysis in one piece, right? Okay, so this slide. R1 parallels R2, right? Then this is the gate 1, yes?
Yes.
Okay. Source 1, RS1 to the ground, yes? Okay. And then to the ground, that's D1. Agreed? Yes? Or I can put P1 here, right? Huh? So you go here. Huh? Yes? Drain 1 is connected. Okay, then what do I do? The gate 2 is connected to S1, right? Gate 2. And then
S2.
S2, RS2, correct?
Correct. And you
And
D2
D2,
is on the ground.
like D2 right here, right? again to the ground.
And V out is from RS2.
And VL is here. Yes. Yes. Okay, now I have to put into the model. So what is the best way to do this? The current source in the model is always connected between where? Between the drain and the source, right? Okay, so here, drain to the source, huh? Yes? Yeah, and always go from the drain to the source, yes? So this is GM1 VGS1, and this is VGS1, yes? Okay. That's it. Okay, we don't have any R's above, okay? Now,
Second one.
drain to the source, yes? Is it?
Yes.
Okay. So, GM2 VGS2, so VGS2. Okay, so that's it. Yes?
But that's different than V out, yeah?
And VL is here.
It looks like it's
VL is from this to the ground, yes? Basically, it's the voltage across RS2, right? Okay. I did not really optimize the circuit, okay? I could make it look prettier. I did not do that, but that's basically what it is. Okay, so VO is equal to the current. This is only a single loop, right? So the voltage must be what? GM2 VGS2 times RS2, yes? Because this current is the same as that current, right? Then we go to V sub I, right? V sub I is what? V sub I is this plus that. Agree?
Yes.
Okay, so it's equal to VGS1 plus the voltage drop on RS2, yes? Sorry, RS1. RS1. And equal to VGS1. What is the voltage drop on RS1? There's a current, right? Which is GM1 VGS1. So it's a GM1 VGS1 times RS1. Correct? Alright? So, now we have V sub I expressed in terms of VGS1, but V sub I is expressed in terms of VGS2, so you need a correlation between VGS1 and VGS2. Yeah? One more equation, then you are done for A sub B. So how do I correlate VGS1 and VGS2? Well, look, there's a loop, right? If I want to, I can go from here, go away, go from here, right? That's a loop, yes? So in this loop, V sub O equal to, because this is minus and plus, right? Equal to what? Huh? Minus and plus, minus V sub O minus VGS2, correct? Huh? V sub O VGS2, right? Minus, and then plus or minus, so that's what? Plus GM1 VGS1 RS1 equal to 0. you see that? Huh? Can you see the loop? From here, going through RS2, right? Going through this gap, which is VGS2, right? This is V sub O. And then going through here, and this is GM1, VGS1. Now, V sub O is here, right? So it's minus GM2, VGS2, RS2, right? Minus VGS2 plus GM1, VGS1, RS1, 0. So now, I have the correlation between VGS1 and VGS2, right? So now I can say, okay, I'm going to take the VGS1 on one side, right? That's equal to VGS2 on the other side times what? Fine. Alright. I think so. Yep. Good. Okay. Now what do? You go ahead and put it here, right? Put it here. So V sub I is equal to GM2 RS2 plus 1 GM1 RS1, right? VGS2. Okay, so that is the first term, huh? Plus the second term times VGS1, the same. Okay, so that's the expression for V sub I. And V sub O is here. So therefore, A sub B is, this is on the top, right? So GM2 RS2, right? VGS2 cancel out. So this is at the bottom. Plus, how pretty. I feel like I'm teaching algebra. Right? All subjects. Algebra. Okay. So everything is known, by the way. Well, of course, I did not tell you the values of GM1 and GM2, right? But you know how to calculate those. GM1, according to my notes, GM1 is 0.46 milliamp per volt square. GM2 is 0.63 milliamp per volt square. Okay? Then you plug in numbers, you'll find that the V sub B is equal to 0.7. Alright? So let's try to find A sub I. Can we? Sub I. So A sub I, that's the current going through the low, right? Which is here. So I sub out, right? Which is the same as what? GM2 VGS2, right? Correct?
Yeah.
Because this current is the same as the current, okay? And what about I sub I? I sub I is what? Is V sub I over R1 equals R2, correct? Now V sub I is known. Right here. Yes? Is so it's GM2 RS2 plus 1 GM1 RS1, yes? This is times VGS plus GM1 RS1 times the same thing. Yes? Did I do anything wrong? Oh, this whole thing has to be divided by what? Huh? This is the whole thing, okay? It has to be divided by R1 imperial is R2. Yes? That's all. Yeah. So then you take the ratio, A sub I, right? On the top, all you have is just what? GM2, correct? And then on the bottom, well, I don't have to do it. You can do it yourself, right? Basically, this cancels out, right? So on the bottom, you can have something. Okay, and I don't have a number for that. All right. So next, let's try to find out what is the output resistance of the amplifier. Okay, so let's try to find out what is R out. Yes? To do that, we have to put a test voltage, yes? And then we would disable supply, correct?
Where do you connect the test voltage?
Of course, you would connect it across the output terminal. Yes? So basically you can say I connect here. Yes? So that is the V-test. And then this would generate I-test, right? So R out will be just V-test over I-test. Okay, so here you can see this is a node, correct? So current I-test equal to what? Yes? Minus GM2 VGS2, right? And then this one is leaving, right? Plus V-test over RS2. Agree? Yes? Now you can make it one flow, okay? Make it easier if you like. So this is one, right? Yes? Okay. Now what do I do? I would have to find the relationship between this and the what? And the V-test, right? So this all the way here, and that, right? And that to the ground. By the way, this is now is grounded, right? It's short. So you see that V-test, right? Minus plus, going through here, minus VGS2, right? And I'm going to go here, right? Again, minus VGS1, and then where? To the ground, 0. You see that? Huh? This, right? I'm going to go from the ground, right? Ground. Okay? Ground here, right? And then this is all short circuit, right? And then here. Yes? And here. then this is ground. So I'm back from ground to ground. Okay, then what else do I do? GM1, BGS1, this. Okay, now if you go from here to the ground, okay, what do I get? I get minus GM1, BGS1, RS1, right? Here to, and then minus BGS1 equal to what? 0, right? This is the loop right here. From here to the ground. Huh? Now, from this equation, I must conclude that BGS1 is equal to 0. Yeah? How can I conclude? Because if you look in here, right? This is BGS1, BGS1.
In factor with VGS.
Yeah, if BGS1 is not equal to 0, this equation would not be true. Huh? Because this and that is some real number, right? So the only solution you have is BGS1 equals 0. Okay, then that go to here. BGS1 equals 0. VGS2 will be equal to minus V test, correct? Correct? So this is 0, right? So VGS2 is minus that. So now I come back to here, right? So I test now is equal to GM2 V test plus V test over RS2.
How's VGS1 work?
Fact.
From here, yeah.
Oh,
Okay, so this, now I can find out what is R, right? R is V test over that. So it's 1 over GM2 plus 1 over RS2. So that is the solution for R. And if you plug in numbers, it's about equal to 1.3 kilo ohm. Yeah? Good. Good finish. About some questions. Now let's go to the maximum output swing, can I? Before we do that, I will have to figure out what are the DC load line and AC load line, yes? Okay. Oh, so you have the circuit, right? If you look at the circuit, the output loop circuit is what? Is VDD equal to VDDS2 plus, we're talking about the second stage, right? ID2RS2, right? So that's the KVL of the second stage. Yes? Okay, based on that, you can try to figure out what are the DC load line and the AC load line, yeah? Okay, the two boundaries, as you know, this one is always what? VDD, which is 10 volts. Is it 10 volts?
Yeah.
Okay. And this one is always VDD over RDC, right? And if you look at the circuit, what's RDC?
It's RS2.
RDC is RS2, right? Which is 6K. So basically the slope is minus 1 over 6K, yes? Okay, then the Q point is located. So what is ID? What is ID2? Right? ID2 is
0.5 million.
5.5. So what is this, by the way? This is 10 divided by 6. Huh? So it's 1.4, 1.5, yeah? 1.5 milliamp. So Q points are a bit lower, right? So it's 0.5 milliamp. Correct? So this is IDQ. ID2. Okay. What about the AC load line? Look at the circuit. There's no capacitor in the output, right? So the AC is the same as DC, right? Same. So AC equal to DC, right? Okay. Then you have to figure out what is the T point. Yes? So basically you want to find out what is IDT, right? IDT. So to find a T point, again you use this equation, right? So dTD equal to dTs2 T plus ID2T RS2. Right? So equation. When you let this T, this is T, right? Okay, then ID2T equal to Kn2 dTs2T squared. So that's the second equation. So you combine the two, you can get the ID2T. So I got about, I'm not sure it's correct, I got about 1.2 milliamp. Right? So now you can see the DC operation range as far as the drain current is concerned. Right? So the DC operation is ranging from 0 to 1.2 milliamp, right? As far as the drain current is concerned. And what about for the AC? For the AC operation, well, the same, right? Because in this case, the AC and the DC load lines are the same, right? So the same as above, right here. Then what is the maximum drain current swing? Right? Basically, you look at the AC operation range, and then you look, then within the range, there are two windows. Yes? You pick up the smaller window. So in this case, the smaller window is what?
0.5.
Is 0.5. Yeah. Okay. Then you have to try to figure out the output voltage swing. Right? So maximum VO swing is the maximum ID swing times what? You look at the circuit. How does the output voltage related to the drain current? It's by a factor of RS2, correct? So RS2. So therefore, you get 0.5 milliamp times RS2 is what, 6K? Yes, right. So you have a 3 volt peak. So that is the maximum. So that is the maximum output voltage you can have without any distortion. Yep. Okay. So homework due next time. Exam on Monday. So next time I'm going to do one more example on the vertical spatial design, and then we'll talk about the exam.